Hello everyone, my name is Mateusz Jurczyk, and today I will be talking about my latest project called Boxbone Reloaded, which is using x86 emulation and taint tracking to discover disclosure of uninitialized memory in operating system kernels. So the agenda for today is first off to briefly start discussing the communication between user and kernel mode in operating systems and what are the common pitfalls that are related to them, and then introduce the Boxbone Reloaded project, the principles behind it, how it works in general, and how it uses the full system emulation to discover any kind of bugs. Then I will talk about the system-specific approaches, which are specific to both Windows and Linux, which are the two operating systems that I analyzed. I will talk about the results in those operating systems, and then wrap up with some ideas for future work on how this project can be extended and improved, and how we can deal with this type of issues in the future. A few words about myself. I am a low-level security researcher, interested obviously in all sorts of vulnerability research and software exploitation. I work at Project Zero at Google. In my spare time, I play in CDFs as part of the Dragon Sector team, and I have a blog and Twitter where I post some of my research as well. So yeah, let's start with some basics very quickly about user and kernel communication. So as you all know, user applications run independently of other programs and independently of the kernel. And whenever they actually want to do something in the operating system, they call into the kernel to request the operation that they want to do. And when they do it, the ring 3 memory, which is the shared memory between the user and kernel mode, is used as the data exchange channel. So this is how it looks on a simple graph. So we have the user mode program, which wants to perform some operation. So it writes input data to the shared user mode memory. Then it invokes the system call, which transfers execution to the system kernel, which then reads the input data, performs some logic, writes output data back, and returns to user space. Then the user mode program reads the output data back and operates on it. So in this presentation, we're mostly interested in these two stages of the system kernel, first reading input data and then writing output data, and especially in the second part. So let's imagine a perfect world where the kernel doesn't have any bugs. So we would like, in this perfect world, for the kernel to only read every memory unit once within the scope of a system call, and then write to it also at most once after it is done with all of the system call logic, do it in a secure manner, and only write data that is intended for user mode. So that is the state of the perfect world that we could imagine, but of course we have reality instead. So these assumptions that I mentioned can be broken in a number of ways. So for example, we can break the assumption that every memory unit is read from at most once. It may happen that memory is actually read more than once. This was the subject of the original Boxbone research that we performed 4 years ago with Genvale Coldwind. And the possible violation is that we have 2 or more fetches from user memory, which may allow some race conditions to break code assumptions, which can lead to buffer overflows, write work conditions, arbitrary reads, all kind of badness. So this original research resulted in discovering more than 40 vulnerabilities in Windows, and yeah, so we wrote quite a few papers on this subject, on both trying to find these kind of double fetches and also exploit them. This research was also presented here at Black Hat. We can also break the other assumptions in a number of ways. So for example, we can have like unprotected accesses to user mode pointers in the kernel. We can have multiple writes to a single memory area, which can also indicate that something fishy is going on in the kernel. We can have reading from the user mode address after already having written to it, which is also kind of fishy, because why would a kernel do it? And there are some other behaviors which can raise an eyebrow. For example, accessing ring 3 memory within very deeply nested call stacks, or with the first enabled exception handler very high up the call stack. These are also some weird behaviors that could happen. But the subject of this talk is actually this part about only writing data that is intended to be used by user mode. So that's what we will focus on. So writing data to ring 3 happens in general in 4 different cases. So we have system calls, which exist in all operating systems that we're interested in. We have IOCDLs, which are also a special case of syscalls, but they have often dedicated output mechanisms, so we can consider them differently a little bit. We have user mode callbacks, which are a mechanism which is specific to Windows and Win32K graphical subsystem. And we finally have exception handling, where the kernel has to build an exception frame on the user mode stack, so then it also writes to the user mode memory. So let's go back a little bit and think about when writing uninitialized memory or some kind of unintended memory to user mode can happen. So we have this easy problem on the example of a fake Windows system call implementation here of writing an uninitialized value of a primitive type variable. So here we have a system call which calculates the multiplication of 2 of a value. And of course, as we can see, the local output value is not initialized if input value is equal to 0. So then we are leaking basically four bytes of initialized kernel stack memory back to user mode. So this, of course, can happen and will happen, but this is not as bad as it seems, because first of all, it's not a very trivial bug to make for developers. Compilers will often warn about instances of such issues. It doesn't leak too much information because it's just a single variable, and it very well may be detected during development as well because it may be a functional bug. So this is not so bad. But we have many other definitely harder problems. So first of all, we have structures and unions, which are used in C and C++. So here in this example, we have a structure which has 3 fields which are being used to output some memory to user mode. So the two of the fields in this structure are initialized because they are used by the system call, but the third one is reserved. So it's not initialized by default, kind of by design. But still, it's allocated in the kernel's stack, and it's still output back to user mode. So it's leaking some data within that field. Furthermore, we have unions which can have fields and types of fields that have different sizes. So here you can see that we have one D word and one Q word, and only the D word is initialized here, which leaves the other 4 bytes uninitialized, and they are also leaked back to user mode in the uninitialized state. And furthermore, we have structures which have padding holes inside. So we have a D word followed by a Q word. But since the Q word has to be 8-byte aligned, the compiler inserts a padding hole of 4 bytes, which in this code are also not initialized properly and output to user mode. So we have, as I said, different problems related to the structures and unions. First of all, they are usually copied in memory entirely using functions such as memcopy and sizes calculated by the size of operator. They have often many fields, so it's either easy to forget about setting some of them, or they may be not set by design. We have padding holes. We have, as I said, different sizes in unions. And worst of all, compilers don't really have too much insight into structures, especially when they are dynamically allocated from the heap or pools, and also because of the fact that they are often copied using functions such as memcopy. Then we have another problem related to fixed size arrays. So here we have an example of a system call which returns the path to the system on file system. And as you can see, we have this huge array which is allocated from the stack, but it's only partially initialized with the relevant string that we want to return. But the kernel still returns the whole array with more than 200 uninitialized bytes inside. And we have a lot of instances of such long fixed size buffers in the Windows kernel, which are used in the exchange of data between user and kernel mode. They are used for paths in the file system, for names, identifiers, etc. And most often, even though these buffers are fixed in size, the length of the content inside is variable, and usually most of the storage used by the array is actually not used at all. And the other problem is that these arrays are often part of structures which makes it even harder to only copy the relevant part of the string to user mode. Also the bad thing about this is that since this array can be very huge, they can also leak a lot of data from the kernel to the user space at once. And then we have yet another problem which is kind of specific to Windows, but not only. So even though we have this system call which only returns 12 bytes in total in 3 magic D words, It allows the user mode caller to specify the length of the output buffer, and it allocates a number of bytes that is requested by the user mode caller. And even though it only writes a limited number of bytes into the buffer, it copies this kernel mode buffer in a whole back to user mode. So we also end up with a lot of uninitialized data here. This is also very common in Windows, as I said. And the interesting thing about this is that this kind of bug may actually enable disclosure from both the stack and the heap in the same affected code, because of the fact that Windows uses an optimization. So for small request sizes, it uses stack buffers, and for a larger one, it uses heap allocations in many cases. And it often leads to large leaks of controlled number of bytes. And the worst thing is that in this particular case, it could be possible for the user to actually be able to specify the size of the allocation that is being leaked. So it may enable an attacker to try to collide with interesting objects in kernel mode memory in order to leak something interesting. So apart from all of this, we have some more factors which contribute to this whole problem. So first of all, neither Windows nor Linux actually pre-initialized allocations on the stack or heap by default. Of course, there are a lot of exceptions, mostly in Linux, such as the caseAlloc function, the GFP0 flag, etc. But in general, allocations are not initialized by default. A recent change in Windows from a few months ago is that some allocations used for IOCTL IO buffers are initialized now, but that is something that was not true 2 months ago. But the general rule still stands. And as you can see here in the screenshot, even the official documentation of the xallocate pull with tag Windows function warns about the fact that allocations returned by this function contain uninitialized memory, and if the code wants to return it to user mode, it has to memset it first. Another factor is that there are no visible consequences of this kind of behavior. So even though C and C++ don't really make it easy for the code to copy data securely between security domains, there isn't any punishment if you fail to do it correctly. So even if the kernel discloses a few uninitialized bytes in one syscall or another, nothing will really crash in most cases. And so no one will discover this bug. And so as a result, if a kernel developer is not aware of this bug class, and they are not trying to actively prevent it, they will probably never kind of find out because the code crashes or something doesn't work. So it's a very silent type of bug. Yet another factor is the fact that it might be not very easy to discover that any leaks from kernel mode are actually taking place, because some of them could be hidden behind the user mode system API. So even though data is actually leaked from the system kernel back to user mode, in general, the original caller of the system API might not see this data at all. So yeah, when it comes to the severity and considerations of these bugs, you can say that they are not very severe because it's just local info leaks. There is no memory corruption taking place, no remote exploitation involved by nature, and etc. But the actual severity depends on what we manage to leak out of the kernel. This can be addresses that we can use for further exploitation of other vulnerabilities, or it can be some sensitive data that we can use more directly to elevate our privileges in the system. But on the positive side, from the attacker perspective, these bugs are mostly silent and transparent, so we can try to exploit them basically indefinitely and very silently without ever worrying about the system going down or someone actually discovering that something fishy is going on. So as I said, these bugs are mostly useful in practice as a single link in a full exploit chains for local privilege escalation, especially given how much effort is actually being put into protecting kernel address space information in Windows. And one real-life example of this would be an exploit found in the hacking team dump 2 years ago. So in order to exploit another vulnerability, they used a pool memory disclosure, which leaked the base address of the win32k.sys driver. And so, yeah, it was used in practice. And at the same time, a few weeks before all of this came to light, a Project Zero researcher Matt Taint also discovered this independently and reported it. So yeah, when it comes to the benefits of this kind of disclosures, you have to consider them separately when it comes to whether they are stack or heap disclosures. So when it comes to stack, these are consistent and immediately useful values because you know, this is the type of data that is being stored on the stack. So we have things like addresses of the kernel stack because of the stack pointers. We have heap addresses. We have addresses of executable images because of return addresses. We can leak the values of stack cookies, which can be then used to exploit a stack buffer overflow. We have some syscall-specific data that is used by services called directly before the leaking syscall. And also, interesting thing is that we can sometimes leak data of interrupt handlers if they happen to trigger in the same context as the exploiting thread. But that's only on Windows 7. On the other hand, when it comes to heap disclosure, we have kind of less obvious memory, because it's not always just pointers to the stack and to executable images, but we have more potential to collide with something that is more sensitive. So of course we have addresses again of the heap and potentially of executable images, but we can collide with virtually allocations of any active kernel modules related to the disk, networking, video, etc. Yeah. Interestingly, there hasn't been too much work within that space on Windows. So according to my best knowledge, people have started to take interest in this kind of issues something like 2 years ago. So we have this one issue in Project Zero Tracker discovered by Matt Taint. Then we have a presentation given by Wandering Glitch last year about several uninitialized memory disclosure bugs fixed in 2015. And we have two more. We have a presentation from this year from Consequest, which doesn't really concern this subject, but mentions that there are some leaks in Win32k user mode callbacks. And also we have this work from just last month from two researchers, which also collided with my research and tried to find some of info leak bugs in the Windows kernel automatically. On the other hand, the problem seems to be much better well known on Linux. So already 7 years ago, Dan Rosenberg apparently went on a rampage and killed several dozen, I think more than 20 info leaks in various subsystems. He presented some of this work in a presentation given by him and Jon Oberide in 2011. And then there are also a lot of other commits provided by different security researchers who discovered this kind of bugs throughout the history. So this problem seems to be much better well known and well understood in Linux than it is on Windows. Probably because of the fact that Linux is open source, so you can more easily find this kind of stuff there. So let's look into the design of the tool now. We'll start with a quick description of Box, because Box-Spawn Reloaded is based on the Box emulator. It's a full emulator developed by Intel. It has a full implementation of the CPU. It has support for all of the latest features of the CPU, all of the extensions such as SSE, AVX, and stuff like that. It also has all basic peripherals, so you can just run a full operating system on this single emulator without any problems. And the good thing is that it also provides an extension instrumentation API, so we can in addition to just running the system, we can look into how it works and we can change its behavior in any way we want. In terms of performance of this emulator, since it's a full software emulator, the performance is not very good. So here we can see that at the point of taking the screenshot, it was executing about 40 million instructions per second, so that's not too much. The longer story is that if we have a non-instrumented guest, it can run up to 100 IPS, which is sufficient to boot a system in kind of reasonable time, which is under 5 minutes. And when we do it, the environment is fairly responsive. We can, use the system, move the mouse, open some applications and stuff like that. When we add some instrumentation on top of that, we have some overhead depending on what instrumentation we write. In my case, in case of Boxbone Reloaded, the performance drop was to around 30 to 40 million IPS, which was still kind of acceptable for research purposes, so I can still interact with the system and get some visible results. But when interacting with Box, we actually have to put a lot of effort into making sure that the logic that we're implementing in the instrumentation is as simple and as fast as possible. So about the instrumentation support in Box, technically it works through macros defined in C++, starting with the bxinst prefix. And we have a lot of callbacks to actually choose from. So we can execute our own code on initialization of the virtual machine, shutdown, before and after executing an instruction, on linear and physical memory access, on exceptions, interrupts, and stuff like that. So we can control everything that is going on in the system. And this enables us to develop virtually any logic that we want to do. So we can count statistics on what instructions are executing and how often. We can trace instructions or trace memory accesses, add metadata, and stuff like that. So here you can see a full list of the instrumentation callbacks that Box provides. And the ones that are underlined are the ones that I used in Boxbone Reloaded. So it's not too many of them. Basically, the most important ones are just the ones triggering before and after execution of an instruction, and the one triggering on accessing linear memory. And the core logic of Boxbone is that we want to taint track the entire kernel address space. And in order to do it, we need to first be able to send taint on new allocations that are being performed in kernel mode, both from the stack and the heap. Then we want to be able to remove taint when memory is freed. Of course, we want to propagate taint in memory, and then most importantly, we want to detect when some uninitialized memory is copied from the kernel space to the user space. Apart from that core functionality, it's also good that we are able to reproduce the bugs and analyze them somehow. So in order to do that, we want to also keep track of all the loaded guest kernel modules, so we know which driver is triggering the bug. We will also want to read full stack traces to be able to deduplicate the bugs, not to run into the same vulnerability all over and over again. Of course, it's good to also symbolize the call stacks to have pretty reports that we can analyze. And finally, we want to break into kernel debugger attached to the guests when an error actually happens so that we can interactively try to see what's going on in the system. Here you can see a representation of the shadow memory. So we have the guest OS memory divided into user land and kernel land. For every kernel land byte, or rather, we have a mapping of a full mapping of the shadow memory corresponding to the kernel land, and then every memory unit is described by a few variables. Of course, we have the taint bit, but also we have information about what is the base address of the allocation that this byte belongs to. We have the information about where this byte was allocated in the kernel and stuff like that. So this shadow memory size is linear in relation to the size of the guest kernel address space. Currently, we only support 32-bit guests, but that shouldn't be really too hard to modify. And some of the information is stored at 1-byte granularity and some at 8-byte granularity. So right now, with my implementation, the size of the shadow memory is 3 times the size of the kernel address space. So we have 6 gigabytes of memory for a Windows guest and 3 gigabytes of memory for a Linux guest. So it can easily run on any host machine that has a reasonable amount of RAM memory. And apart from just tainting the memory that is being allocated in our shadow memory, what I wanted to do is also pad the guest memory with some special marker bytes. So we have a padding with the AA byte for heap allocations and BB byte for stack areas. This is used mostly, first of all, in order to eliminate all false positives, because now we have the guarantee that if shadow memory indicates that there is a bug, we can also refer to the actual guessed memory and see if these original marker bytes are still these values of AA or BB. It can also trigger some use of uninitialized memory bugs that are not just info leaks, but also other bugs. About setting Taint on stack, this is actually very easy because all allocations performed on stack are performed using the same assembly pattern, so it's cross-platform. What I do in my instrumentation is I just detect these three instructions of adding, subtracting, and ending against the ESP register. And then after the execution of this instruction, if ESP decreased, that I just sent the Taint on the whole new memory region that was allocated this way. Of course, you can imagine cases where this would crash the operating system if it didn't perform properly, but fortunately both Windows and Linux do, so this behavior doesn't crash anything and it all works out. On the other hand, setting Taint on heap and pool allocations is completely different. We cannot do it universally in any way. We actually have to know how the system allocates memory, where the allocators are located in the kernel address space, and how they work. So right now we can just say that after we detect an allocation and we know the address and the size of the allocation, we just taint it. And I will talk about how we do it specifically later in the presentation. Then we want to remove Taint on heap free, which is also very reliant on how the heap implementation works on the specific system. But basically, when we break on a free function prolog, we loop up the allocation size of the memory that corresponds to the address, and we just clear all of the Taint and metadata that corresponds to the whole memory region. Another idea would be to skip this clearing of the Taint and instead retaint this memory in order to detect use after free and leaks of freed memory. But that's an implementational detail. The hardest part of all of this is the Taint propagation, because we can easily detect allocations, but detecting data transfers and handling them correctly is definitely the hardest part. So in case of my project, I only propagate Taint for the repmovsd and repmovsb instructions, which correspond to the memcopy kind of construct. It's used both in the memcopy implementation of various C clients, and it's also used as an inline version of the memcopy function. And the good thing about handling this specific instruction is that we know the source and destination addresses at the same time. So we know how many bytes are copied from which address location to which one. So we can analyze this very easily. And of course, this is only a best effort approach. It's not perfect. We don't handle all of the data transfers, but it still gives us a lot of information, and we still mostly care about copying large memory blobs and not single variables. So this lets us to spend as little time on this with as much benefit as we can get. And it also has quite a small CPU overhead. So if a memory access is not a result of this instruction that we specifically analyze, then we perform the following steps. If this instruction that we encounter is writing to some memory, we just clear the Taint on that memory area. And if the instruction is reading from the memory, we check the Taint information. And if the shadow memory indicates that this is actually an uninitialized read, we verify whether this is the case or not with the marker bytes that I mentioned before. In case there is a mismatch for whatever reason, we just clear the Taint again. But if the marker bytes are still there in the guest memory, we report the bug. And also, the real detection of the user mode or kernel mode information leak triggers on the repmovsb instruction, where the ESI is in kernel mode and EDI is in user mode, which is a very clear indicator that uninitialized memory is actually copied from kernel to user mode. So once we have all of this information and this picture of how this project should look like, we can try to run it on some real systems, starting with Windows. What we have to do first is we have to implement the tainting of pool allocations. In Windows, we have a lot of functions which allocate memory from the pool. All of them start with xallocate pool, but there are different variants. But fortunately for us, all of these functions eventually call into one called xallocate pool with tag. And it's very convenient because it uses the std calling convention, which means that we have the arguments on the stack and the return value in EAX. And this means that when the read instruction is executed in this function, we have all of the information about both the allocation request and allocation result at the same time. So this is very convenient for us. This is how it looks on a graph. So we have different callers of all of the allocation functions. Eventually, they all call into xallocate pool with tag. And then we break on this single read instruction and read all of the relevant information from EAX and from memory under ESP. So we read where the allocation is being made from the return address and the requested size and the allocation tag for some debugging information. And then we also break on the x-free pool with tag function, this time in the prologue of the function, and we just read the address of the region that is being freed in order to clear the taint. Unfortunately, there are some corner cases which we also have to take into account in order to find all of the bugs. So, for example, in Windows, we have some optimized specialized allocators, such as the one used by Win32k. So there is this allocator which, first of all, tries to return a cached memory region that is pre-allocated, and after only it is busy, the actual Windows kernel allocator is used. So, and it's called from quite a few locations, so we have to take care of that. But what we can do is we can just simply patch this function to always use the system allocator instead, and we're good to go. When it comes to propagating taint and detecting bugs in Windows, we're quite lucky because the memcopy function that is used by the Windows kernel actually uses the repmovsb and repmovsd function instructions. Sometimes they have some optimizations that we have to care about. So, for example, in Windows, if the copy size is less than 32 bytes, then mov instructions are used instead of repmovsb or repmovsd, but we also can just modify that in assembly. So in general, as a result, tracking most transfers of data blobs in Windows works out of the box with the approach that I mentioned before. I'm not sure. Oh, you can actually see that quite well. So I created a small visualization of the whole address space in Windows 7. So here you can see the whole 2 GB kernel address space over time. This is an image which is of dimensions 1024 by 512. Each pixel is a single memory page, and so these pages that have some stack memory taint are marked in green, and the pool ones are marked in red. So now we can see that what the patterns are in Windows when it boots up and when you start some of the applications in Windows. So that's 40 minutes of runtime. A new snapshot was being taken every 20 seconds here. So I find that quite interesting myself. And here you can see the similar image on Windows 10. Over 120 minutes with a snapshot taking every 60 seconds because the boot time was much longer on the box emulator. So you can see that much more memory is consumed by the operating system, and the patterns in which memory is allocated is also quite different. When it comes to other technical details, such as keeping track of processes and threads, it's very simple. It's the same as in the original box spawn from 4 years ago. It's just about traversing a single linked list of modules in the kernel address space. And the same goes for keeping track of loaded kernel modules. You also just have to go through a list of descriptors and note the values there. So here we have an example of box spawn that was generated in an actual runtime. So you can see all of the information that we have about the bug that happened. We have the address of the memory that is being read. We have the information about the process. In this case, it's explorer.exe. We have the faulting instruction, which, as I mentioned before, can only be repmovsd in this case. And we have information about where the memory region was allocated. In this case, it was just a generic function inside of Win32k, and the stack trace of where this happened. So this is all very good, and it looks very nice, but it was a very simple example, and there are much more complex examples where we have a bug, but it's not just 2 stack frames, it's actually like 30 stack frames, because the bug happens inside of an IOCDL handler, someone very deep inside of the kernel. So it's not very convenient in that case to try to analyze the bug based just on the single box spawn report. So as I mentioned before, what I wanted to do is to be able to attach WinDBG or WinBag to the emulated guest kernel. And this is not a very big problem because Box actually supports redirecting COM ports to Windows pipes, so we can just enable kernel debugging in the guest system and then attach a WinBag to it from outside. Of course, this is very, very slow. If you try to attach WinBag, it takes maybe 5 minutes for it to fully initialize and provide with the interactive shell, but it's still workable for our purposes. Of course, this is not sufficient because even though we have this kernel debugger attached, we don't know when the bugs are happening. So what we also want to do is that we want to break on the specific moment when a bug happens. And this is achieved by injecting an in3 instruction in the emulator exactly at the moment when the bug is detected. So this lets us break into the debugger and see exactly what is going on and what memory is being copied to user mode and why. So for me, at least, it seems it feels quite magical that it all works, but it does. So here we have a screenshot of a WinBag attached to the Box guest here. Yeah. When it comes to the testing that I performed in order to get some reasonable code coverage, first of all, I run the instrumentation against Windows 7 and Windows 10 in order to get both the old code that could have been removed in Windows 10 and also the new code that was added in that system. And within that guests, what I did is that I, of course, booted up the system, started a few default applications such as Internet Explorer, WordPad, stuff like that. I generated some network traffic, and I also ran so-called React OS unit tests, which is a bunch of applications which are used by React OS to test whether the behavior of the system is the same as Windows. So it actually helps us provide or get a lot of code coverage in the kernel that we wouldn't be able to do otherwise. We already used these tests 4 years ago, but they largely improved since then, so they were very helpful for us. But of course, even though we did all of those things, it's still not the perfect amount of code coverage that we can get, so it's still a major roadblock in every effective usage of full system instrumentation because we can find only as many bugs are actually triggered on the system. So let's look into the results. This is the results on a single slide. So it's a couple of screenshots from Microsoft bulletins from the last 4 months. The summary is that we found so far 30 vulnerabilities. 13 of them were from the pools and 17 from the stack. So it's quite evenly divided. And we can see here the pool ones were triggered in a number of kernel drivers. So we have both the core NTS OS kernel, we have Win32k, we have a bunch of, partition manager drivers, volume manager drivers, stuff like that. And the root causes of those bugs are also very diverse. So we have bugs caused by structural alignment, Unicode string alignment, padding holes, and a lot of different things. And also the amount of bytes that were leaked is also quite diverse. So it ranges from just a single byte to over 6 kilobytes of information at a single request. And then we have the stack disclosures as well. From a number of functions. They are also diverse. For some of them, I wasn't really able to figure out what the reason for the leak was. But yeah, it's still quite a lot of them, so it's an important problem. Once we detect these bugs, we want to reproduce them, of course. And this is another important problem that we have to look into. So In order to reproduce the pool info leaks, what I did is that I used a regular VM in order to make sure that this bug is not specific to Box, but also a normal environment. What I did is that I just found out which driver was making the allocation that is being leaked to user mode, and I already had this information from the metadata. I enabled special pools for that module, reboot the system, and then started the POC twice. And then I could observe a repeated marker byte at the offsets where the data was leaked. So this is how it looked like for the volume disk extent vulnerability. When I run it the first time, you can see 39 marker byte, but then when I run it again, it's another byte. So you can easily see where the leak is actually taking place here. When it comes to stack info reproduction, that is much more difficult because there is no official or documented way of padding stack allocations with marker bytes. But on the other hand, we still want to reproduce these bugs reliably and be able to show where the bytes are being leaked, because otherwise, first of all, it's easier for Microsoft to find to fix those bugs, and also it's easier for us to make sure that the bug is real and also reproduce outside of the test environment. What we can do in this case is that we can use stack spraying. This is a technique that allows us to spray the kernel stack with some controlled memory. And it works thanks to the fact that Windows uses optimization of using local buffers for small requests. And some of the system calls actually have very large buffers for storing optimized local data. So we have this system call called anti-map user physical pages, which allows us to put 4 or 8 kilobytes of controlled data on the stack. So it's very convenient. So this is illustrated here. First of all, what we do is that we just spray the kernel stack with some easily recognizable patterns, such as the 4.1 byte, and then we trigger the vulnerability, and we see where this marker byte happens to be in our output buffer. So this is another example of running the anti-GDI get realization info POC here, which leaks 8 bytes from the kernel stack. And a quick digression is that if memory marking can be used for bug demonstration, it can also be used for discovery. That's what I at least thought. And the basic idea would be to, first of all, enable special pools for all of the kernel modules, and then invoke the tested system call twice, pre-spraying the kernel stack with a different byte each time. And then we can compare the output of the system call and see if it differs in a reliable way. And the perfect candidate to test in this way is the family of anti-query information system calls, which have a very common structure. So we have a handle to the object that we want to query. We have some information class, which is just a simple integer. And we have a pointer and size of the output buffer. So we can create the object that we want to query, and then we can just brute force pretty much both the information class and the expected buffer size. And there are about 10 such functions which we can test this way. So this looked quite promising, and indeed it turned out that this was a fruitful idea, and I was able to find about 5 bugs this way as well. So it was quite easy. So in summary, the problem seems to have remained mostly unrecognized until now, probably because of the factors that I mentioned before, that it's quite invisible and not obvious to find these bugs. But on the other hand, it's a fundamental issue which is trivial to overlook, but very difficult to get right in the code. So I think it's also a tip of the iceberg. So even though I found 30 bugs so far, there are hundreds of memcopy calls to user mode in the Windows kernel, and every one of them is a potential disclosure. So there are still probably a lot of such bugs lurking in the code base of Windows. And this is especially true in the cases where the size is user-controlled, but the amount of relevant data is fixed or otherwise limited. There are some mitigations ideas that Microsoft could probably implement in some way in order to try to mitigate those bugs. First of all, of course, they could just memset all stack and pool allocations when they are made or requested, which would make the bug go away without doing any bug fixing at all. But of course, that is probably incurring too much of an overhead, so it's not realistic. And especially given the fact that most kernel allocations probably don't end up copied to user mode anyway. But it turns out that Microsoft implemented a part of this idea by mem-setting the buffered I/O output buffer in the IOCTL implementation just a few weeks ago. So they are definitely looking into this. There are some other mitigation ideas that are more realistic, such as, for example, clearing the kernel stack between system calls. They could also add a new allocator function, which just clears the return memory regions before returning them. They could also just detect which allocations end up being copied to user mode and then only clear those, either automatically or just by adding memset calls manually. And in general, since Microsoft has the Windows source code, they could bring this idea to a whole new level by writing better instrumentation, which has more information about data transfers and stuff like that. They also have probably mode code coverage that I am able to achieve by just running a few simple tests and starting a few applications, which also means more bugs found. And static analysis is also easier to use to guide these dynamic approaches. So when it comes to closing remarks for Windows, of course, this box spawn approach could be also used to detect regular use of uninitialized memory, but the results in case of Windows are much harder to triage because we don't have access to the source code, so we cannot easily analyze if this use of uninitialized memory is an actual bug or not. And another point that I wanted to make is that the subject of leaking specific sensitive data from pull disclosures is still an interesting subject that hasn't been explored too much. Now, I also wanted to talk about running box spawn against Linux, but I guess I don't have too much time anymore. So I will just quickly say that the tainting of heap allocations is much more difficult on Linux because the allocators themselves are plenty. It's not just a single function, but we have a couple of families such as kmalloc, vmalloc, kmemcache alloc, and stuff like that. All of them work in different ways. So we have a lot of these functions for kmalloc, a lot of these functions in vmalloc. We have to hook into most of them in order to be able to catch all of the allocations. In my case, it was 7 of them. We also have problems such as the fact that we have a different calling conventions with arguments passed through registers and not the stack. So instead of just hooking into a single read instruction, we actually have to hook into both the prologue of the function in order to save information about the allocation request, and then we have to hook into the return instruction in order to be able to read the address that it was being allocated, and then we can set the taint. Then we have this troublesome family of kmemcache functions, which create a cache of allocations which are initialized and tainted at the time where the object is initialized, but not at the time when it is requested. So we have to implement some additional logic to account for that. Other than that, we have a few flags that we have to set in the config in order to make the memcopy function be compiled into a set of rep movsb instructions. We have this visualization of Ubuntu memory layout, which I'm going to skip right now. We have a few other config options that we also have to set in order to enable debugging symbols, use the right kernel, user address mode split, and disable some of the mechanisms that we don't want to use in the emulation. Then we also have to set another config option to make sure that copy to user, which is used to copy memory back from kernel mode to user mode, is also compiled into repmovsb and repmovsd instructions. Unfortunately, there is one problematic function that we have to also care about, which is put user, which is a macro used to copy simple types back to user mode. But we can take care of that by just using a hack of using these prefetch instructions in order to enable and disable strict mode in box, which means that we just sanitize all of the reads from memory that happen between those two instructions. You are welcome to ask me about the details of that after the presentation, but that's how it looks in assembly. So we have the prefetch 1 and prefetch 2 instructions, and in between these instructions, we just sanitize all of the memory reads. So yeah, we have a very similar log from Boxbone report right now. So it's all the same information about the instruction, the stack trace where the bug happened, and stuff like that. We also have a kernel debugger attached as well, so we can debug these bugs that happen at runtime. We performed some very simple testing as well by running a few system call fuzzers such as Trinity plus I know this, also a few unit tests such as the Linux test project, and a couple of other things. Unfortunately, we weren't able to use syscaller because it's currently only supporting 64-bit architectures, and we were working with 32-bit. When it comes to the results, they are much less impressive than on Windows. So it was just a single bug, which was very minor because it was in the IOCTL of a device that was only accessible to root. I still discovered it around April 20th, and I was still going to report it a few days later, but when I started looking around, seeing if anybody has reported it already, I discovered that 7 days after I discovered it, someone from Google already have fixed it, so too bad. But since that didn't work out so well for me to detect just the direct kernel to user info leaks, I decided that I could enable the global strict mode and detect all uses of uninitialized memory and analyze all of them, because I had access to the source code in this case, so I could just look into the in-depth root cause of every such instance. So I did that, and this was more lucky for me, so I was able to find a few bugs. One of them actually led to the discovery of an actual kernel info leak in the LLCP sock connect in NFC sockets. The other ones are much lesser. They were still uses of uninitialized memory, but not directly leading to information disclosure. Thankfully, all of them have been fixed now. And as you can see, some of them have also been found by external researchers as well. So it turns out that when it comes to uninitialized reads from kernel mode, my project was not the only one in Linux. So there is a project called Kernel Memory Sanitizer, which is being worked on right now. It's called KMSAN. It's developed by Alexander Potapenko, and it has collided on a few of my findings. And the important thing is that it's actually working in a different way. It's adding instrumentation at compile time. It's very similar to projects such as Address Sanitizer, Memory Sanitizer for user mode, and this is the correct way to do it in Linux. But I still wanted to also test my approach on that operating system. So the conclusions in terms of Linux is that here we have a community which has been on top of the problem for the last few years. We don't have so many info leaks here. And even if we find something, it turns out that these bugs seem to be quite short-lived, from my experience at least. Yeah. There is a little bit of future work to be done here. We can run further iteration on Windows. We can try to look into improving code coverage, which is always something that needs to be done. I can also think about improving taint propagation beyond just rep of SB, and implementing support for 64-bit guests, which also should be able to identify a few more new bugs. There are some other more crazy approaches, such as taintless approaches of not having any taint, but only looking into writes into user mode memory and seeing if there are any marker bytes that are being leaked there. This addresses the problem of non-ideal taint propagation, but it has other problems as well. Yeah. We can also think about detecting leaks not just into user mode memory, but into other things, such as outgoing network traffic, file system metadata, and stuff like that. So there is a lot of work to do still, but I think the results so far are still quite impressive and are motivating to look into info leaks more in the future. So thank you for listening, and I'm happy to answer questions.